Good day, everyone. I am Rafa, and we are the group DENDEN and Friends from the Bachelor of Science in Civil Engineering Block 2B. And our topic that we'll be discussing for today is all about angles and directions which are needed in surveying. So, the content of our report consists of the following topics. First, we're going to discuss about angles. What are the different angles, their types, and how do we solve for these angles? Second will be all about directions. What are meridians, prime meridians, longitudes, and the such. Third will be all about the differences between azimuths and bearings. Fourth will be the types of compasses and their uses. And lastly, what is a compass survey? So for our introduction, for us to locate an object with a reference to a known position, we generally need three things: the horizontal length, the elevation, and the angular direction. Both the horizontal length and the elevation can be measured by using differential leveling or the other levelings that were previously discussed by the third reporters. And lastly, the angle between two converging lines is what we call the angular direction. If we have the lines of the elevation and the horizontal length that are converging, then the angle between these converging lines is what we call the angular direction or the angle. So what are angles? Angles are defined as the difference in direction between two converging lines. So angles measured in surveying are classified as either horizontal or vertical angles, depending on the plane in which they are observed. If the plane is observed horizontally, then the angles are classified as horizontal angles. But if the surveyor is observing in the vertical plane, then the angles are said to be vertical angles. So the instruments used in surveying that are able to measure the angular direction are the theodolites and the total stations. The theodolite is a telescope that has both the horizontal and vertical axis, and it can measure fairly accurate positions of angles as long as the surveyor knows how to use the theodolite. The total station, on the other hand, is an instrument based on electronic distance measurement or EDM and can measure distances, elevation, as well as angles with a high level of precision. And if one were to ask which instrument would better measure angles at a high level of precision, then one would say that it would be the total station because the theodolite can measure angles at a minimum range about less than a kilometer and are less precise when compared to total stations. The total stations, on the other hand, can measure angles with a minimum range of about 1 kilometer and are very precise, hence making it more expensive when compared to theodolites. So the angles formed by the direction of two objects in a horizontal plane is what we call horizontal angles. In the picture, we have a horizontal plane with objects B and C along their respective lines that are converging at the instrument at A. The angular direction, or alpha, will be the horizontal angle that we'll be measuring. So horizontal angles is used primarily to obtain relative direction to sort a survey control point, which allows engineers to establish surveying works from connecting these two control points by determining the horizontal angle. More so, horizontal angles can be used in topographic detail points or points to be set out, especially in traverse. And usually, horizontal angles are measured with a theodolite or a total station whose precision ranges from 1 to 20 seconds of arc. So seconds are one of the unit measurements used in determining the angles, while the other two are the degrees and the minutes. The degrees are the largest unit of measurement used in determining the angles, while the smallest one is the seconds. So the unit system used in determining the angular direction follows a sexagesimal system which divides the circle into 360 degrees, in which a degree is equivalent to 60 minutes and 1 minute is equivalent to 60 seconds. So if we have a full circle that has a measurement of 360 degrees, then to convert it into minutes is to follow the conversion of 1 degree is equivalent to 60 minutes and 1 minute is equivalent to 60 seconds. So always remember that the first number that you will see is in degrees, while the second is in minutes, while the third is in seconds. So in horizontal angles, it is also important to talk about its different types and their distinction. In horizontal angles, we have different angles. We have the interior angles, exterior, and deflection angles. So in surveying, surveyors use polygons to conduct surveying work, and mostly they refer polygons as traverse to help establish control points. The angles inside the traverse or the polygon are what we call the interior angles. So interior angles are the angles within the closed polygon of n number of sides. If we have a polygon of 5 sides, then it is expected that we have 5 interior angles from the converging lines of our polygon. Also, we can determine the summation of all interior angles by simply using the formula n minus 2 times 180 degrees, where n represents the number of sides of the polygon. In this example, we have 5 sides, so the value of n is 5. If we have a polygon of 3 sides, the value of n will be 3, and the total summation of the interior angle is 180 degrees, since 3 minus 2 is 1, and 1 times 180 degrees is equal to 180 degrees. Using the same example for a 5-sided polygon along with established interior angles of station A, B, C, D, and E, we can simply use the summation formula with n being 5 to get a total of 540 degrees. But if you want to verify that your work is correct, the total summation of all the angles can also be determined by adding all the individual angles at the different stations, and you will still get a value of 540 degrees. Take note that the angle is also in minutes, so we have to convert minutes into degrees. So adding all the minutes, we get a value of 120 minutes, and we convert it into degrees, so we get 2 degrees. So 2 plus 538 degrees is equivalent to the total summation of all the interior angles, which is 540 degrees with 0 minute and 0 seconds. So the next type of horizontal angle is what we call the exterior angles. These are the angles outside the traverse of polygon. So if we have this station at B, the angles outside of that station is what we call the exterior angles. So exterior angles are measured occasionally to serve as a check on the interior angles. Usually, we measure the exterior angles to check whether the interior angles is correct or not. We can also say that the relationship between the interior and exterior angles will form a whole circle because when we add these two, both the exterior and the interior angles, it will form a 360-degree measurement. Also, using this relationship, we can determine the exterior angle by subtracting the interior angle to 360 degrees. We can also determine the summation of the exterior angles by using the formula n plus 2 times 180 degrees. Remember, in the summation of interior angles, the formula was n minus 2 times 180 degrees. But in the case of exterior angles, instead of minus, we now have n plus 2 times 180 degrees. Take note that the summation from this formula with the summation of all exterior angles will be greater than the summation of all the interior angles. So the next type of horizontal angle is what we call the deflection angles. Deflection angles is a horizontal angle that is observed from the extension of the back line to the forward line measured either going to the left or going to the right. And to better understand its definition, here we have an open traverse that can be represented with the different route stations at its edges. This is an example of an open traverse because the last station, which is here, ends somewhere else except from its starting position. The main difference between this traverse and the previous one is that the other one is a closed traverse since the last station ends where it started. But this is a closed traverse, so the last station ends somewhere else except from its starting position. So in order to get the deflection angle, the first thing we need to do is to make an extension line of the backline. And this can be done by simply extending the backline forward. So if this is our backline, we have to extend this backline forward and this becomes our extension line. And the angle between the extension line, which is this one, and the forward line, which is this, is what we call the deflection angle. And for our example, we see measurements 22 degrees and 18 minutes R. R refers to the direction in which we measure the angle. Since we started from the extension line going to the forward line, R then moves in the clockwise direction. So similar to the first station, the back line will be extended. However, the forward line of the previous station will now become our back line, and from the extended back line of the new station, the deflection angle can be measured by measuring the angle between the extended line and the forward line. Since the direction is going to the left, L refers the counterclockwise direction, thus obtaining 38 degrees and 6 minutes L. And in this portion, this line over here will now become our back line, and we have to extend it forward. From there, we will measure the angle in between the extended line and the forward line, thus having a measurement of 17 degrees and 51 minutes R. R because it is in the clockwise direction since we measure the angle from the extended line going to the forward line. Also, it is important to remember that deflection angles are always less than 180 degrees, and that the deflection angles must clearly be identified as being turned either to the left or to the right using the letters L or R respectively. More so, deflection angles are commonly measured during open traverse or route surveys such as highways, and they are used principally on the long linear alignments of route surveys. So other than the horizontal angles, we also have vertical angles. These are the angles measured in the direction of gravity. There are two types of vertical angles, one of which is the traditional vertical angle or just the vertical angle. The traditional vertical angle is measured up or down from a horizontal line. And in the figure, we see that the vertical line ranges from negative 90 degrees to positive 90 degrees above the horizontal line. The angles above the horizontal line is what we call the angle of inclination, while the angles below the horizontal line is what we call the angle of depression. So another type of vertical angle is what we call the zenith angle. The zenith angle is measured from the upper end of the vertical line that continuously goes all the way around to form a circle. And in the figure, the zenith ranges from 0 degrees directly upward or above the observer going to the 90 degrees on the horizontal and to the 180 degrees directly downward. The 180 degrees downward angle is what we call the nadir, and it is located below the observer. And from the nadir, it goes to the 270 degrees on the opposite horizontal and goes back to the zenith at 0 degrees. In this figure, it shows a combination of vertical and zenith angle circles with an instrument at their center as a reference, zenith angles being blue and the verticals being red. This figure helps us understand how the two types of angles relate to each other. So the conversion between the vertical and zenith angles is pretty simple as long as one thing is remembered. A vertical angle is ambiguous while a zenith angle is not. So what does this mean? In the figure, we have lines AB and AC that both have a positive 25-degree vertical angle but different zenith angles because at line AB, it has a zenith angle of 65 degrees, while at line AC, it has a zenith angle of 285 degrees respectively. And to convert from a vertical angle to a zenith angle requires knowing which side of the zenith circle is involved. So traditionally, from the 0 degree going to the 90 and to the 180 degrees side of the circle, it is an instrument's direct position, while at 180 degrees going to the 270 and back to 0 degrees, it is the side of the reverse position. And to show the relationship between the two, we will perform a few example conversions. So in example number 1, we have to convert a 56-degree 40-minute zenith angle to a vertical angle. And as with most surveying problems, a sketch would help us visualize the problem, and this will be our sketch right over here. So, knowing that the zenith angle starts at a 0 degree above the observer, we will then move to the 56-degree mark. We know that from the 0 degrees going to the horizontal line, it measures 90 degrees. And from this measurement, we will deduct it from the given. And take note that the given is also a unit in minutes. So if we deduct 56 to 90, we will get a value of 34. And from this value, we will then take 1 degree of our initial answer and convert it into minutes. And knowing that 1 degree is equivalent to 60 minutes, so 60 minus 40 minutes, 40 is from the given, and the answer would be 20 minutes, thus giving a vertical angle of 33 degrees and 20 minutes. And since the angle is above the horizontal, then the vertical angle is then positive. So moving on to the next example, we have to convert a 227-degree 30-minute zenith angle to a vertical angle. And again, to help us solve the vertical angle, a sketch will be utilized to solve the problem. So this is our sketch right over here, and our given angle is at this portion of the circle. So similar to the first station, we must establish that from the zenith angle of 0 degrees going to the opposite of the horizontal, it measures 270 degrees. And from this measurement, we will deduct it from the given angle of 227, and it will give us a value of 43 degrees. And since the given is also a unit in time, we must take 1 degree of our 43-degree measurement and convert it into minutes. And knowing that 1 degree is equivalent to 60 minutes, so 60 minus 30, 30 being the given is equal to 30 minutes. We then have 42 degrees and 30 minutes. But because the angle is below the horizontal, the vertical angle should be negative. Thus, our final answer would be V is equals to negative 42 degrees and 30 minutes.
Hi guys, I'm Denise Domingo and I'm going to be talking about directions. Survey geographic reference. Surveying involves measuring the location of physical land features relative to one another. This means that a reference point would be necessary in order for us to obtain a location of a certain point. For example, if a surveyor wishes to determine the location of point B, as seen on your screens, he should measure it with respect to point A, which in this case is our reference point. Apart from this, it can also be relative to a defined reference on the surface of the Earth. So as stated a while ago, in order for us to define an unknown location, a relative reference point would be needed. However, a global reference point is more important. We are able to identify our global reference point through the utilization of the Earth's reference system. The Earth's reference system is composed of the surface divisions denoted by geographic lines of latitude and longitude. These lines are used together to specify the geographical coordinates of a location on Earth. Take note that the lines of latitude run in a horizontal direction from east to west, while lines of longitude run in a vertical direction from north down to south. Positioning on the Earth's surface. The difference between longitude and latitude lines. Longitude lines are imaginary lines that run around the Earth vertically. These lines are called meridians, and they meet at the south and north poles. Longitude is an angular measurement, and we express it in degrees. We measure the distance around the Earth as 360 degrees, and each meridian measures 1 degree of longitude. Therefore, there are 360 meridians. Negative longitudes are west of the prime meridian, while positive ones are east. Speaking of the prime meridian is set as 0 degrees longitude, and it divides the Earth into the eastern and western hemispheres. The meridian opposite to the prime meridian is the 180 degrees longitude and is known as the anti-meridian. Modern timekeeping systems use longitudes as references to timekeeping. Time zones are defined by the prime meridian and the longitudes. On the other hand, we have the latitude lines. Latitude lines are imaginary circles parallel to the equator. They are also known as parallels. Unlike the longitude lines, latitude lines actually never meet because by definition, lines of latitude all run parallel to the equator around the world. There are 180 such imaginary lines. Each line measures 1 degree north or south of the equator. Therefore, we express them in angular measurements from 0 degrees at the equator to 90 degrees north or south. The equator is an imaginary line perpendicular to this axis, and it represents 0 degrees latitude. In addition to the equator, there are 4 other major latitudes that are usually found on maps and globes. The positions of these latitudes are determined by the Earth's axial tilt. The first one is the Arctic Circle. It is an imaginary circle drawn around the northern part of the world at approximately 67 degrees north. All locations falling north of this latitude are said to be in the Arctic Circle. The next is the Antarctic Circle. It is an imaginary circle drawn around the southern part of the Earth, parallel to the equator at approximately 67 degrees south. Any location falling south of this latitude are said to be in the Antarctic Circle. Places in both the Arctic and the Antarctic Circle experience the midnight sun and the polar night. The third one is the Tropic of Cancer. The Tropic of Cancer is an imaginary line around the Earth approximately 23 degrees north of the equator. It marks the northernmost position on the Earth where the sun is directly overhead at least once a year. This happens during the June solstice when the Earth's northern hemisphere is tilted towards the sun. And lastly, we have the Tropic of Capricorn. It is an imaginary line around the Earth approximately 23 degrees south of the equator. It is the southernmost position on the globe where the sun is directly overhead during the December solstice. As seen on the picture, combining both latitude and longitude lines gives us a reference system on the Earth's surface. Thus, we can locate each and every location on Earth basing on them. Magnetic north versus geographic north. So as we all know, the Earth rotates or spins on its axis, and the two ends of the axis are the geographic poles north and south. This is also known as true north and true south, or geographic north and geographic south. But we also have a magnetic north and a magnetic south. The Earth acts as a giant magnet with north and south poles, but these points are not exactly where the axis of rotation or the true north and south is. So there is a difference between the two at the poles. So how they differ is that geographic north is the direction towards the fixed point we call the North Pole, while the magnetic north is the direction towards the North Magnetic Pole, which is a wandering point where the Earth's magnetic field goes vertically down the planet. The geographic north differs from the magnetic north by about 500 kilometers. The geographic north is where lines of longitude converge into what we call the North Pole, while the magnetic north is a point in northern Canada where all the northern lines of attraction enter the Earth. A compass needle will point the direction of the magnetic north. The Earth's magnetic north is changing every day because of the hot liquid metal that surrounds the inner core. It can change so much that the Earth's magnetic field can flip polarity. This is called the polar reversal theory. The following are important definitions and terms related to the topic. First is meridian. Meridian is a fixed reference line or direction which lies in a vertical plane passing through a fixed point of reference and through the observer's position. Next is true meridian. It is sometimes known as the astronomic or geographic meridian. It is the generally adopted reference line in surveying practice. This line passes through the geographic north and south poles of the Earth and the observer's position. Third, we have the magnetic meridian. It is a fixed line of reference which line parallel with the magnetic lines of the force of the Earth. Its direction is defined by freely suspended magnetic needle of a compass held at an observer's position. Next, we have the assumed meridian. It is an arbitrarily chosen fixed line of reference which is taken for convenience. This meridian is usually directed from a survey station to an adjoining station or some well-defined and permanent point. It is used only on plane surveys of limited extent since they are difficult or may be impossible to re-establish if the original reference points are lost or obliterated. Next, we have the magnetic declination. So the magnetic poles are not points but are oval areas located about 2,000 kilometers away from the actual location of the geographic poles of the Earth. These areas are not fixed and may move to a different location every day, perhaps as far as 50 kilometers. The horizontal angle, direction, and direction by which the needle of a compass deflects from the true meridian at any particular locality is called the magnetic declination. And lastly, we have local attraction. Local attraction is any deviation of the magnetic needle of a compass from its normal pointing towards magnetic north. In the field, the compass user may not realize that the magnetic bearings read with the compass have been affected by local attraction.
In this slide, we are going to be talking about bearings and azimuth comparison. A bearing is the measurement of an angle that always gives an acute angle. Bearings are designated by the direction of either north or south first, then east or west. Types of bearings include forward bearing and backward bearing. Based on the picture shown, which shows the measurement of line AB, the forward bearing is found at A to B. Forward bearing is described as the line in which the direction of the survey progresses, while backward bearing is found in the opposite direction of where the survey progresses. This means that it is measured from B to A. In the next slide, we are going to be talking about azimuths. Azimuths is the term used for the measurement of an angle with respect to the reference meridian, which is north. The measurement of the angle is always in the clockwise direction, and the angles range from 0 to 360 degrees. For the conversion for azimuth to bearing and bearing to azimuth, we can use this example. In this example, we see that the angle is found in the southeast quadrant and gives the measurement of 55 degrees. We can say that the bearing of this example is south 55 degrees east, and the azimuth of this example is 145 degrees. So, when you're given the azimuth and not the bearing, it is important to identify the different quadrants for defining a bearing, and taking note that the reference should either start with north or south, depending on the given, then followed by east or west. When given the bearing and looking for the azimuth, it is important to take note of our knowledge in angles and that we should start at the reference meridian, which is north. In this example, we can see that the first quadrant is equal to 90 degrees. And since the bearing is at south 55 degrees east, we can add 90 degrees and 55 degrees to get the azimuth of 145 degrees.
Good day everyone, my name is Levin and I'm going to talk about the types of compass and their uses. So to measure and define angles and directions, we use an instrument called a compass. There are several types of compass. The first compass is the Brunton compass. It is one of the most versatile and widely used compass. It combines the features of a prismatic compass, sighting compass, hand level, and clinometer. So for the uses, it is used for general navigation. Just like any regular compass, it has a needle that points to magnetic north. It is suitable and sufficiently accurate for preliminary and exploratory surveys, engineering type surveys, and topographic surveys, requiring only low degrees of precision. It measures as well the strike and dip of rock layers. Dip is the acute angle that the cross-sectional rock surface makes with the horizontal plane. Strike is the compass direction that the bed is running. So on the right side, we have the parts of a Brunton compass. We have the small sight, center line on mirror, sighting window, round level, long level, circular scale for reading direction, index pin, peep sight, large sight, semi-circle scale for reading vertical angles, vernier arm for vertical angles, needle lift pin, declination adjustment screw, and magnetic needle. Here we have the lensatic compass. It is a compass that consists an aluminum case containing a magnetic dial balanced on a pivot. a hinged cover with a sighting wire, a hinged eyepiece containing a magnifying lens for reading the dial graduations, and a sighting slot for viewing the distant object. It is used to determine azimuths. It is also used to follow a course over the ground, orient or set a map, and determine position of objects in relation to a map. It is a compass used often in war. It has helped to save many lives and provided many with recreational and commercial usefulness in times of peace. It is designed for military use, such as in reconnoitering, determining directions, artillery fire directions control, and other uses where magnetic azimuths are required. Here we have the parts of a lensatic compass. You have the sighting slot and lens for the rear sight, thumb loop, floating dial, bezel ring, graduated straight edge, sighting wire, luminous sighting dots, fixed index line, short luminous line, and luminous magnetic arrow. Next, we have the surveyor's compass. It is a compass that has a compass box containing a graduated circle, two sight vanes, a magnetic needle, and two clamping screws. A glass cover protects the needle and the graduated circle. It is an instrument for determining the horizontal direction of a line with reference to the direction of a magnetic needle. The instrument can either be screwed onto a tripod or remain handheld for the purpose of measuring magnetic bearings. It was popularly used earlier for running limited plane surveys of reasonable accuracy. Now it is commonly used for forest surveys, in retracting old land surveys, and in geological explorations. So for the surveyor's compass, we have the vanes here, guide vane, magnetic needle, fixed graduated plane, screw, circular metal box, and a bubble tube. Then we have the plain pocket compass. It is similar to the surveyor's compass except that it has no sight vanes. It is used in reconnaissance and exploratory surveys. It is a small hand instrument used for obtaining roughly the bearing of a line. The compass is useful for experimental purposes or for direction finding in desolate parts of the countryside or during the darkness and foggy weather. So we have the scales here, base plate, direction of travel arrow, magnifier, index point, dial, declination marks, orienting arrow, orienting lines, needle, and the housing. Next, we have the prismatic compass. For the prismatic compass, the graduations are found on a rotating card instead of being on the compass box like a surveyor's compass. The card moves with the needle since both are fastened together. Two short sighting devices are provided and magnetic bearings are read by means of a prism at the same instant that the compass is sighted along the line. It is used to measure the angles known as bearing, and the distance are measured using a measuring tape. It is widely used by sailors for navigation at sea. This compass is used for solar observations or for viewing any very high object, and is not a normal fitting to a compass. The two circular discs in front of the back vane are dark glasses, which can be swung in front of the vane when solar observations are being taken. Here we have the objective vane, horsehair sliding arrangement for mirror, graduated ring, glass cover, prism, sunglasses, eye vane, eye silt, eye hole, hinge, hinge tap, focusing stud, metal box, lifting lever, lifting pin, hinge, and adjustable mirror. Then we have the forester's or hand compass. It is a compass which is usually made of aluminum or some type of metal that does not affect the free movement and positioning of the magnetic needle. It is widely used in forestry surveys as well as for geological and other similar exploratory surveys. It is a compact magnetic compass capable of one-hand use and fitted with a sighting device to record a precise bearing or azimuth to a given target or to determine a location. Another hand compass is also called a marine hand bearing compass. It enables you to take a magnetic bearing on a distant object. This bearing allows you to plot lines of position for coastal navigation. Last but not the least is the transit compass. It is similar to the surveyor's compass, only it is mounted on the upper plate of the transit. It is used for orienting the transit with a magnetic meridian. It is a specialized instrument used widely by those needing to make accurate navigational and slope angle measurements in the field. It is used to check horizontal angles and directions measured or laid off during transit surveys. Now let's talk about the common errors and mistakes in compass work. First, we have a bent needle. It is when a compass with bent needle is used. All observed bearing will have a constant error. Next is the errors in reading the needle. It is due to the inability of the observer to determine exactly the point on the graduated circle where the needle comes to rest. Another source of error is if the plane of sight is not vertical. The line of sight may be steeply inclined. Next is the local attraction. The correct pointing of the magnetic needle toward magnetic north is usually affected by different forms of local attraction, thus creating errors. Lastly is the bent pivot. The magnitude of the error will depend upon the direction in which the sight is made. For the mistakes, we have when the observer is reading the wrong end of the magnetic needle. Next is if the observer is not releasing the needle completely and not allowing it to swing freely about the pivot. Lastly, we have mixing or interchanging the recording of azimuths from north and south, magnetic and true bearings, clockwise and counterclockwise angles, or forward and back bearings. Next topic is compass surveys. The method of compass surveying is one of the most basic and widely methods of determining the relative location of points where high degree of precision is now required. Such surveys, which employ magnetic compass, are performed by traversing. First, let's have the definition of terms. Traverse. A traverse is a series of lines connecting successive points whose lengths and directions have been determined from field measurements. Traversing. It is the process of measuring the lengths and directions of the lines of a traverse for the purpose of locating the position of certain points. Traverse stations. Any temporary or permanent point of reference over which the instrument is set up. It is usually marked by a peg or a hub-driven flush with the ground and identified by consecutive letters or numbers as the survey progresses. Traverse stations are sometimes called as angle points because an angle is usually measured at such stations. Traverse lines. These are lines connecting traverse stations and whose lengths and directions are determined. We have two types of compass traverse. First is the open compass traverse. An open compass traverse consists of a series of lines of known lengths and magnetic bearings which are continuous but do not return to the starting point or close upon a point of known position. Then we have a closed compass traverse. A closed compass traverse consists of a series of lines of known lengths and magnetic bearings which forms a closed loop or begin and end at points whose positions have been fixed by other surveys of high precision. Here we have the summary of the procedure for adjusting a closed compass traverse. We will use some of the formulas discussed earlier in the presentation. First, using the forward and backward bearings, create the closed compass traverse figure. Then we determine all the observed interior angles. Next, using the formula n-2 times 180 degrees, we compare the sum of the computed observed interior angles and the theoretical sum of the interior angles. Fourth, we solve for the MPVs of the interior angles, discrepancy, and correction. Fifth step, we adjust the forward and backward bearings based on the best line considered and the MPVs of the interior angles. Next step, we check if the forward and backward bearing is back to its original direction and is numerically equal. Next, you can check your solution by doing the same process of adjustment to the best line. And if the answer is the same as the forward and backward bearing, which you consider the best, your computations are all correct. Lastly, we put all your output in a tabular form. Thank you everyone for listening. Once again, we are Denden and Friends. Stay safe and God bless.